Hi folks, welcome to today's video on numerical derivatives. Should match okay closely with 2.3.1 in the AP Calculus CED. So let's take a let's remind ourselves of something that we've been taught previously. So earlier in the semester we estimated the slope of a curve by using the right-hand difference quotient with delta x equals 0.01. So the difference quotient might have looked something like this. Well, it would have been x plus some small value, 0.01, minus f of x, all over x plus 0.01 minus x. Well, that's just going to give us 0.01. I did a little bit of that in my head there. X plus 0.01 minus x, and the x is canceled. So basically that's our difference, our right-hand difference quotient. We can also do a left-hand difference quotient, so we would say something like x minus 0.01 minus f of x, and that would be over negative 0.01. And there I just did a little bit of subtraction. I said x minus 0.01 minus x, so I combined the like terms. X minus x was 0, so you just have this negative 0.01 as a result. And then a symmetric difference quotient, so maybe I go a little bit to the right of our given point, so x plus 0.01, and then maybe x minus 0.01. And then when I subtract those on the bottom, I would have x plus 0.01 minus, parentheses, x minus 0.01. The x's would indeed cancel, but the 0.01 would be added to another 0.01, giving me 0.02. And each method usually gives an accurate estimate of the derivative, but we will use something similar to the symmetric difference quotient if given a table of values. And I'm going to change this just slightly. We will most of the time mostly use something similar to the symmetric difference quotient. Okay? So anytime I have one of those for all cases statements, I feel like I need to say, let's say most of the time. Okay? So here goes some examples. This first example just says to find the average rate of change on the interval from 0 to 5. So that would be f of 5 minus f of 0 over 5 minus 0. F of 5 is 34. F of 0 is negative 1. So it's basically 35 over 5. Sorry, 35 over 5. And that is 7. Okay? The next piece says to estimate the derivative at 2. Estimate f prime at 2. Well, there's 2. And we need to do some kind of derivative. And we know that the derivative is the limit as delta x, or let's call it h, as h goes to 0, of a difference quotient. Okay? Wait a minute. So we can't really do all that, right? Now, if I did a difference quotient, I could say this f of x plus h plus a little bit, and then maybe x minus h, so minus a little bit, and then I'd have 2h in the denominator. So instead of thinking of it as a derivative strictly by using the formula, why don't we just look at the idea? The idea with this table is that I could go a little bit to the right and just use that point. So basically f of 3 minus f of 1. And that's exactly what we want you to do. Over 3 minus 1. So f of 3 is 14, f of 1 is 2. So essentially I'm getting 12 over 2, and I apologize for doing more than one step in one step, but there it is. So f prime of 2 is approximately 6. So in order to estimate the value of the slope at 2, we just find the slope of the secant around that point 2. That includes the point 2. Okay? If I want to do the same thing for f prime, this would be a good time for you to pause the video if you haven't yet. But you would do the same thing. You would just say a little bit to the right, so go to f4, go a little bit to the left, f2, so over 4 minus 2. F of 4 is 23, f of 2 is 7. 23 minus 7 gives you 16, and 16 over 2 is 8. Okay, so that's exactly how you can estimate the value of a derivative. So the previous problem had pretty much no context. In this example here, we do have some context. We say that x is some distance in centimeters, and temperature is T of x, and it's some degrees in Celsius. So it says to find the average rate of change from 0 to 8. So like we did in the previous problem, we'll just do T of 8 minus T of 0 over 8 minus 0. And T of 8 is 55, T of 0 is 100, and I just need my calculator for that computation there. It looks like it's negative 45 over 8, but I am checking in a calculator. And it is negative 45 over 8. And we can leave it this way. And basically what it means is that it went down 45. Now we're thinking T's on top, so those are degrees. So degrees, it went down 45 degrees over a time span, over a distance of 8 centimeters. Okay? So this says using correct units, explain the meaning of the ARC. And ARC is just average rate of change there. All right, so correct units, explain the meaning. Well, that means, you know what, let's convert that to a decimal. Let's divide by 8. Okay, so basically I'm getting negative 5.625, and it is degrees per centimeter. Okay, so explain the meaning of the average rate of change. This just means that over the time interval, or I'm sorry, the x interval, over the x interval 0 to 8, the temperature decreased on average 5.625 degrees per centimeter. Okay? So over the x interval 0 to 8, the temperature decreased on average 5.625 degrees per centimeter. Okay, I like the way that is stated. Maybe I can become a little bit more clear as we practice more. So I should point out that there could be some times during these intervals to where it's not exactly 5.625, negative 5.625. Actually, most of the time it's probably not negative 5.625. It's just guaranteed that negative 5.625 is somewhere in there. Okay? So anyway, let's move on to the next page. Okay, so this says to estimate t prime at 7. Well, t prime at 7, well, there is no 7 in my graph. There's a 6 and an 8. So we have the point 6, 22, sorry I read that wrong, 662, and we have the point 855. Okay, so those are the 2 points that I'm going to use. T prime is approximately T of 8 minus T of 6 over 8 minus 6. T of 8 is 55, T of 6 is 62. And 55 minus 62 is -7, and -7 over 2. And then we're going to indicate units of measure, so we're going to say degrees Celsius per centimeter. Okay? And then it says to explain the meaning of T prime at 7. I think I'll save that. Instead of recording this on video, I'll save that for you guys. T prime at 4 and indicate units of measure. Well, this time 4 is in our table. Oh, I'm sorry, it's not. But it is between 1 and 5, so I'm going to use 1 and 5. So 193, 570 are my 2 points that I'll use. 193, 570. Okay? And at this point in the video, I feel like I'm being a little bit repetitive, so I'm going to leave those to you. Now, there is a function on your calculator that you will want to have handy. Okay? The symmetric difference operation is built in to your TI-84. It's known as inderiv. I like to call it Math8. Okay? So what we want to make sure of is that your calculator in calculus is always in the radian mode when you're using trig. Mine is in radian mode. If that's not highlighted, you would just push enter on that. Okay, so from there, we're just going to type in Math8, and it brings up Leibniz notation, and you type in the DD, you have to type in X. That X button is up here. So next to the alpha key, you don't push alpha to get it, you just push that key, and then you're going to type in x squared sine x, and exactly like it is, and then it says where is x, what is x equal to? Well, x is equal to pi over 2. And we type that in, and check us out. We just found f prime at pi halves, and actually it looks like it equals exactly pi. 3.14159. Yep, that is exactly pi, actually, and that should be at least entertaining to you, and it might be more entertaining as we learn more differentiation rules. So find the derivative using your calculator. So we're just going to go into the Math8. We'll just type in x 4 to the 0.35 x over, I'll need a fraction bar. I'll just push the division symbol instead of writing the big fraction bar like I try to do during the videos. So x to the third, and this is at x equals 1.65, and we just type that in. So we just found f prime at 1.65 to be equal to -0.661. And rounding to the third decimal place is most appropriate in AP Calculus. Third decimal. All right, so that's all for this video. I showed you a little bit on how to use tables and also how to use the Math8 function in your calculator. We talked about how we can use the symmetric difference property when we are given, or the symmetric difference quotient, in order to estimate derivatives when we're given a table of something like f of x. Okay. Also, I never mentioned how you could use a right hand or a left hand, but let's consider what if the question said estimate what the slope is, estimate f prime at 5? Well, if you're given the table, then you only have 5 and 4 to use, so that's the case where you would use a left-hand difference quotient. And another time it might say find the derivative at 0, or estimate the derivative at 0, or in other words, estimate the tangent line at x equals 0. And in that case, I only have a point to the right of it in my table, so I would use the right-hand difference quotient for that one. All right, so that's all there is for numerical derivatives. I hope you enjoyed that video and got a lot out of it. Let me know. See ya.